In statistics, the way you pick your sample can literally make or break your results. Today, we're diving deep into one of the most fundamental methods out there, simple random sampling. We're going to unpack the math, the mechanics, and the absolutely crucial differences between sampling with and without replacement. All right, so here's what we've got on tap. We'll kick things off by defining what sampling with replacement even is. Then we'll get into the real nitty-gritty of its mathematical properties. After that, we're going to have a little showdown, sampling with replacement versus sampling without it, to see which one comes out on top. And we'll wrap it all up by learning how to calculate the perfect sample size using a really practical example to make it all click. Okay, first things first. Let's build our foundation. What exactly do we mean when we say simple random sampling with replacement? We'll call it SRSWR for short. The big idea here, the absolute key, is independence. Picture this. You've got a hat full of names. With this method, you draw a name, you read it, and then you put it right back in the hat. That means every single draw is a totally fresh start. The full population of n units is always there, so every single unit always has that exact same 1 in n chance of being picked. Now, this process might look super simple. Pick, put back, repeat. But that one little step, the act of replacement, it has huge consequences for the math. Because we put every item back, it is entirely possible to pick the exact same unit more than once in our final sample. And that possibility of repetition is what really defines this whole method and shapes every formula that comes next. Okay, so we've got our sample, now what do we do with it? Well, we use it to estimate things about the whole population, and these two formulas are our main tools. Let's break down that first one, y bar r, which is our estimate for the mean. We take yi, that's the value of a specific thing, like, say, the height of a person. Then we multiply it by qi, which is just how many times that person showed up in our sample. We do that for everyone we sampled, add it all up, and divide by n our total sample size. The second formula is way easier. To estimate the population total, you just take that mean we calculated and multiply it by n, the total number of people in the population. Simple as that. All right, now let's pop the hood and see how this thing really works. To have any faith in our estimates, we have to understand their statistical properties. And believe it or not, the key to all of this is that little variable we just met, Q, the count of how many times each unit appears in our sample. Okay, this is where we get into the mathematical guts of it. That variable Q follows what's known as a multinomial distribution. The first couple properties make perfect sense, right? The expected or average count for any unit is just our sample size n divided by the population size n. The variance tells us about its spread. But look at the covariance. That's where the really interesting insight is. See that negative sign? That is so cool. It tells us that the counts of different units are negatively linked. So if you happen to sample unit A more often than you'd expect, you have to be sampling unit B less often. It makes total sense because your sample size n is fixed. So you might be looking at that covariance formula and thinking, where on earth did that come from? Well, we're going to prove it, and it's actually pretty clever. We're going to tackle the same problem from two completely different angles. The first angle is to treat the counts of two units, qi and qj, as one single blob. The probability of picking either one of them in a single draw is just the probabilities added together. That means the total count of i's and j's follows a simple binomial distribution, and we have a standard formula for its variance, which is what you see on the screen. Okay, that was the first angle. Now for the second. This one uses a fundamental rule from probability. The variance of a sum isn't just the sum of the variances. It's the sum of the variances plus 2 times the covariance between them. And the magic here is that this version has the exact thing we're looking for, the covariance of Q and Qj sitting right there in the formula. And this is where it all comes together. We have two different ways to write the exact same thing, the variance of Qi plus Qj. So what can we do? We can set them equal to each other. We already have formulas for the individual variances of Qi and Qj, so we just do a little bit of algebra, expand the terms, cancel things out, and we're left with a beautifully simple result for our covariance, negative n times pi I times pj. And for the grand finale, that formula we just figured out works for any sampling probabilities. But we're in a special case, simple random sampling, where the probability of picking any single unit is always 1 over n. So we just plug 1 over n in for both pi and pj, and bam! We've just mathematically proven the exact formula we started with a few minutes ago. Pretty neat, right? So after all that math, what's the actual payoff? It's this. Our estimator for the mean is unbiased, and that is a huge deal in statistics. It means that while any one sample might give you an estimate that's a little high or a little low, if you were to do this over and over and over, the average of all your estimates would land exactly on the true population mean. Your estimator doesn't systematically aim too high or too low. It's right on target, on average. This table sums up that awesome property and gives you the variance formulas you'd need. All right, time for the main event. We've gotten a handle on sampling with replacement. But what about its more popular cousin, sampling without replacement, or just SRS? Now, in stats, when we say a method is more efficient, we mean it has less variance. It gives you a more precise, less noisy result. So let's have a showdown. Which one wins? Let's just put the variance formulas right next to each other. At first glance, they look almost identical, don't they? That s squared over n part is exactly the same. The entire difference comes down to that one little piece in the numerator. For sampling without replacement on the left, it's n minus n. For sampling with replacement on the right, it's n minus 1. And you don't have to be a math whiz to see what's happening here. As long as your sample size n is bigger than 1, that n minus n term is always going to be smaller than the n minus 1 term. And because that term is smaller, the entire variance we're sampling without replacement is always going to be smaller. The verdict is in, and it's crystal clear. And here is the bottom line, the big takeaway. Sampling without replacement is just flat out more efficient. The intuition is really simple when you think about it. When you don't put the name back in the hat, every single person you pick gives you brand new, unique information. You're not wasting any of your precious sample size remeasuring someone you already have data on. So if you have the choice, you should always sample without replacement. It buys you a more precise estimate for the exact same amount of work. Okay, so theory's great, but let's get down to brass tacks. We know which method is better, but that brings us to maybe the single most common question any researcher has to ask. How big does my sample need to be? Let's figure it out. This formula right here is the engine that drives almost all sample size calculations. It's basically a balancing act between three things you have to decide on. First up is Z, which is all about your confidence level. Most people use 95% confidence, which means a Z-score of 1.96. Second is S, the standard deviation. That's a measure of how much variety there is in your population. More variety means you need a bigger sample. And third is E, the margin of error you can live with. How precise does your final answer need to be? A tiny margin of error means you'll need a huge sample. Now, that first formula kind of assumes your population is infinitely large. But what if it isn't? What if your first calculation tells you to sample, say, 20% of your entire population? Well, then you get to use this awesome little trick called the finite population correction. It essentially gives you credit for having already sampled a big chunk of the population, and it lets you reduce your required sample size. It's like a discount that can save you a ton of time and money. All right, enough with the abstract stuff. Let's roll up our sleeves and walk through a real-world example. Imagine we've got a cookbook, and our job is to estimate what proportion of the recipes have 0 animal products in them. First, let's lay out what we know. The total number of recipes, our N, is 1251. We want to be 95% confident, so our Z-score is 1.96. And we want our final estimate to be within 3 percentage points of the true value, so E is 0.03. Now, the tricky part, we need the variance, S squared, but we don't know it yet. So what do? We play it safe. For a proportion, the variance is at its absolute maximum when the true proportion is 50-50. It's the most uncertain situation. So we use P equals a 0.5 as a conservative guess, which gives us an S squared of 0.25. This guarantees our sample will be big enough. So we take all our numbers, zeta is 1.96, S squared is 0.25, E is 0.03, we plug them into that initial formula, we crunch the numbers, and it spits out a result. We need a sample of 1,067 recipes. Whoa, hold on a second. Look at that number. Our entire cookbook only has 1,251 recipes. This formula is telling us we need to check more than 85% of the entire book. That seems insane, right? It's totally inefficient. This is the perfect time for our friend, the finite population correction, to come in and save the day. We take that initial oversized number of 1,067 and we plug it into our correction formula. And boom, the new, adjusted, much smarter sample size is just 576. Let that sink in. We just cut our workload almost in half. We saved ourselves the time and effort of checking nearly 500 recipes, and we did it without losing a single drop of our precision or confidence. That is the power of using the right statistical tools.
That whole example really shines a light on a classic statistical dilemma. To figure out our sample size, we needed to know the population variance. But how can you know the variance of a population you haven't even sampled yet? It's a classic chicken and egg problem, right? So what on earth do you do in the real world?
Luckily, statisticians have a few clever tricks up their sleeves. First, there's the play it safe method, which is exactly what we just did by assuming the proportion was 0.5. It guarantees your sample is big enough. Second, you could run a small pilot study, maybe sample just 30 or 40 recipes to get a rough first guess at the variance. Third, you can often borrow from the past. Look at data from older, similar studies to get a reasonable starting point. And finally, there are more advanced methods, like using the coefficient of variation, which lets you define your error margin in a slightly different way. And that really brings us to the end of the road here. Sampling theory isn't just a bunch of formulas to memorize for a test. It's a toolkit for making smart, strategic decisions. It's all about designing research that is both statistically powerful and actually possible to do in the real world. The real skill isn't just knowing the math. It's using that math to carefully balance the never-ending trade-offs between precision, cost, and feasibility every time you start a new project.